Okay, good morning, and thank you for coming to this. This is the last seminar of this official cycle of the Institut of the Estructura de la Materia, and it's for me a great pleasure to introduce you to Professor Stéphane Colin from the INSA, is the National Institute of Applied Sciences of Toulouse. Professor Colin is an engineer and PhD from the Polytechnic Institute of Technical
of Toulouse.
He is specialized in fluid mechanics. He was then assistant professor in the Université Paul Sabatier in Toulouse before becoming a professor at the INSA. And he's a specialist in gas in microfluidics. He covers all aspects from theoretical modeling, experiments, and fabrication, design and fabrication of micro devices. He's also the founder of the work group in gas microfluidics within the French Society for Hydrothermic, and is a co-chairman of the European Microfluidics Conference. And he will talk today about gas flows in microfluidic microsystems from the theory to applications. When you want.
Okay, thank you very much for the introduction and the invitation. I am pleased to speak today about gas flows in fluidic microsystems. My presentation will have several parts. I will start with a rapid history about microfluidics and speak about the market. Then I will focus on microfluidics with gases, and I will first show you the main theoretical point linked to this problematic domain. Then we will speak about experimental analysis. There would be a lot to say about that, but I will focus my talk on velocimetry, and I will finish by showing you a specific example of microsystem we are working on, which is a Knudsen pump. So a very short story about microfluidics. We can start in 1840 with Poiseuille, who was the first scientist to measure liquid flow rates in very small microtubes, 10 microns in diameters. He was doing that for better understanding the circulation of blood in the human course. And with 10 microns in diameter, the Poiseuille law, which is a simple link between the flow rate and the pressure difference at both ends of microtube, was still valid. But if he was able to go down in size, maybe he would have seen some unexpected phenomenon that have been further studied in microfluidics. The second, so it is Poiseuille. The second point was the first time you can read about not microfluidics but fluidics in the literature. Fluidics was a term invented in 1958. It was during the Cold War between USSR and USA, when they were fighting to be the first to dominate space. And at this moment, computers were not still invented. Computers were very big. They were consuming a lot of energy. They were heating a lot, and they were not really compatible with a space system. So the idea at this moment was to replace electronic computers by fluidic computers. So a lot of specific elements were developed, able to make all specific operations that make a computer. Instead of managing a flow of electrons, you were managing a flow of gas. And a lot of small systems that were fluidic elements, like this one, were able to make addition, subtraction, multiplications, logic control, and so on. and fully pneumatic computers were able to make some complex operation. For example, this kind of gas circuit, it only needs some gas under pressure, was able to make an operation of dividing by 10. If you put an impulse flow rate of gas at the outlet, you have 1 impulse over 10 inlet impulses. So if you want to see this device, it was made in 16, and it was preliminary to microfluidics. But it was named fluidics. In 1959, Richard Feynman made a very famous lecture. The title was "There is plenty of room at the bottom." The idea was to develop microsystems to make something that bigger systems were not able to do. And this famous lecture paved the way for the development of micro-electromechanical systems. The first real micro-electromechanical systems were in 1980. They were not dealing with fluids at the moment. And the first time we can see really the word microfluidics was around 1990. It was the first development of some microsystems with mechanical parts, with fluids, with electronic, and so on. But the real development of the market on microfluidics was in 2005, more or less. So a rapid outline, you can see here the previous steps that were necessary to be able to build some very small devices, some microelectromechanical systems, but it is on this second line that really microfluidics is starting with various devices. First, just to have a flow of liquid, then to have two-phase flows with what we call digital microfluidics. Each droplet here can be a microreactor in which you can have a reaction between different things, living cells and so on. In 2010, 2005, there are the first attempts to build organ on chips to reproduce the functioning of some organs. And the first 3D printed micro device appeared around 2010, but gaseous microfluidics is a quite new domain that appeared around 2010, because most of these applications were first with liquids. So if we want to speak money, as I mentioned, the development of microfluidics started in 2008, and you can see that there was a very rapid growth in the market, mainly for pharmaceutical, medical, veterinary applications. And at the beginning here, it was less than $1 million. In 2016, it was already $4 billion. And the increase has continued with a level of $25,000 billion expected in 2025. And you can see that the applications are drug delivery, diagnostics in medicines, point of care diagnostics for humans, and so on, but not only, as we will see. And if we have a quick look at the forecast market of microfluidics in 2027, the volume should be more than $30 billion. So what about the materials what are used to build these microsystems? The first one were silicon, because the idea comes from microelectronics, and the first material to be microfabricated with high precision was silicon. Then a lot of development have been made with glass, and more recently, most of the systems have been made with different polymer. In terms of cost, you can see that it's a significant part. In terms of number of device units is larger, because the cost of polymer-based microfluidic systems is much lower than, for example, silicon-based microsystems. So, and just to make a short focus, these microsystems can be used as actuators or lab-on-chip, as sensors. And if you are focusing on sensing, the first sensing devices were connected to image for CMOS sensors for cameras. After that, in 2010, there were a lot of developments for microphones, microspeakers at a very small scale. Then last developments were on the touching for your smartphones, for example. And now we are more in this sense, which is smell, and for developing electronic noise sensors for analyzing some specific species in the environmental air. There is a real important need of specific microfluidic systems, and we are now in applications dealing with fluids and specifically with gas. And you can see the last expectation for microsystems for test and sense. So you have seen that gaseous microfluidics is quite recent. It's in the 10 last years, and there is still, it's an emerging field, but there is still a lot of application. For example, you can have a micro-heat exchanger for cooling electronic components or for chemical applications. Micronozzles can be used to make a thin orientation of microsatellites, but we can also find this kind of micronozzle in more complex systems, such as microgas analyzers. This is a micronozzle for mass spectrometry. This is a total system, a microgas chromatography system, including a pump, a chromatographic loop, and a system to analyze gas species. But you can also find microsystems for controlling large flows. It's a domain of active flow controls. You can, on the wing of a plane, have a series of micro jets that are connected to microsensors and can act on the boundary layer around the wing, and they can delay the detachment of this boundary layer, increase the lift, reduce the drag, and also reduce the noise. There are a lot of research made using this microjet, micro oscillators, and so on. I will speak at the end of my presentation about Knudsen micropumps used as vacuum generators. You also encounter microflows of gas in some sensors, pressure, temperature, mass flow sensors, and also more recently on so this is a vacuum pump, on organs on a chip, such as artificial lungs. So what is the theoretical problematics linked to microfluidics? The main question is a question of rarefaction. If you consider a gas, you have to consider a series of specific lengths. The first one is the mean molecular diameter. The second one is the mean distance, mean molecular spacing, mean distance between two molecules. The most maybe important one is the mean free path of the molecules, the mean distance traveled by molecules between two statistically between two consecutive collisions. And you have to compare this free length with a characteristic length of your system. For example, if it is a channel, it can be the diameter of this microchannel. In order to give some figure, if you consider gas at standard conditions, the mean molecular spacing is around 3 nanometers. And if you consider a specific gas, for example, air, the order of magnitude of diameter of the molecules is 0.4 nanometers. And the mean free path is around 50 nanometers. So you have 3 orders of magnitude between the diameter of the molecules, the mean spacing, and the mean free path. And they should be compared to this typical length. When the system is high, you can consider that the gas is a continuum medium because there are a lot of collisions between molecules. They are able to exchange information such as their temperature, their kinetic energy. But when you decrease the distance, you have less collisions between gas molecules and more collisions between the gas molecules and the walls. And there are two consequences. The first one, if you have in this space not enough molecules, you cannot define statistically macroscopic quantities such as pressure, temperature, and velocity. Roughly, in a sampling volume, you need about 10,000 molecules to be able to start neglecting the microscopic fluctuations. So it's necessary to have a certain volume. The second point is the mean free path. If the mean free path is not small compared to this dimension, you will not have enough collisions between molecules, and you can have some discontinuities in terms of temperature, in terms of pressure, and so on. And the hypothesis of continuum model cannot work anymore. So if we want to have a clear picture of all this, it's quite complex. But we can focus on one single parameter, a dimensionless parameter, which is Knudsen number. And the Knudsen number is the ratio of the mean free path divided by a characteristic length. Once again, if it's a channel, you can take as a characteristic length the hydraulic diameter. And it can be shown that when you increase the Knudsen number, you will change the regime of the flow. Up to a Knudsen number of 10 to the minus 3, classic flow modeling is perfectly matching. You can use Navier-Stokes continuum equation. You can use classic boundary conditions that say that the fluid has no velocity at the wall and that there is a continuity between the temperature of the gas or the liquid, but here it's the gas, on the gas and the wall. If you increase the Knudsen number between 10 to the minus 3 and 10 to the minus 1, you can still consider that far from the walls you have a continuum medium, but in a short layer, which is called the Knudsen layer close to the walls, there is a local thermodynamic disequilibrium, and it will lead to a slip of velocity and a temperature jump between the gas and the walls. And if you go further, here you can completely you should not consider any more a continuum model. So Navier-Stokes equations, Fourier equations are no longer valid. It's a complex domain to model. And if you increase still again the Knudsen number, it's a free molecular regime. It's more easy to model because you can completely neglect the collisions of gas molecules between each other. So to give an order of magnitude, if you consider a microchannel with a square section, if you consider air in standard condition, you will see that if you go below a dimension of 100 microns in width, you enter in this specific slip flow regime. And most of the microsystems that works in standard conditions are in this range of dimensions. So this regime is of very high interest. But of course, you can have systems a bit higher in dimensions. If the pressure is lower, you will also change the mean free path. So you can increase the mean free path, increase a bit the characteristic length, and be also in this range. And if you decrease the dimensions and also simultaneously decrease the pressure, of course, you will increase the rarefaction effects. So last point, this mean free path can be linked by the appropriate collision models to the viscosity, the density, and the temperature of the gas. And the classic Reynolds and Mach numbers are also linked to these parameters. So if you make a link between Reynolds Mach number and the mean free path that is used in the definition of the Knudsen number, you can see that there is a close link between these three dimensionless number. Knudsen number is linked to rarefaction, Mach number is linked to compressibility, and Reynolds number is linked to the competition between viscosity and inertia of the flow. So you cannot touch one of them without touching the other. And typically, when we decrease the dimensions, we don't have a significant effect of the compressibility of the gas, but we increase the viscosity effect. The flow can rapidly come from a turbulent flow to a laminar flow. So the Reynolds number will decrease, and simultaneously the rarefaction, thanks to the Knudsen number, will increase. Okay, so I will now focus on this regime where there is a velocity slip and a temperature jump. It can be demonstrated that between a wall and the gas, you will observe a velocity slip, a difference between the velocity, the tangential velocity of the gas, and the velocity of the wall. Generally, this velocity is 0. There are different terms, two terms here. The first one is called the viscous slip, is linked to the value of the mean free path and to these two gradients, the transverse gradient of the tangential velocity and the other gradient, the longitudinal gradient of the transverse velocity. This viscous slip will increase the mass flow rate because you will not have a zero velocity at the wall. It will consequently increase the convectivity transfer, and it depends on a specific coefficient, which is called the viscous slip coefficient. Another interesting term is the thermal creep or thermal transpiration terms, which is due to a temperature gradient along the wall. It doesn't need any pressure gradient to generate a flow at the level of the wall. You just need a temperature gradient, and you have here what we call a thermal slip coefficient. And if we speak about the temperature jump, you have something similar to this equation. This temperature jump will decrease heat transfer, and we need to know for modeling correctly this temperature jump, a temperature jump coefficient. So we can rapidly see what is the origin of this different phenomenon. The viscous slip, we can have a very basic information. For sure, if you have a wall which is a reflective wall, when the molecules is arriving in this direction, if the wall is perfectly flat at the level of the molecule, which is not possible, it will go back with an angle equal to the incident angle, and you will keep the tangential velocity of the molecule. So the tangential velocity here is not zero. But in most of the cases, the wall is a diffuse wall. The roughness is not negligible compared to the size of the molecules. And when a molecule arrives like that, it can go in any direction. So we can say that more or less, in average, it will go perpendicularly to the wall, so without any tangential velocity. But even in that case, the mean velocity at the wall is not zero. Because what we call the mean velocity at the wall is the average velocity from the molecules coming from the wall after collision at the wall. The tangential velocity here can be zero, but you have also some molecules coming from here at a distance more or less equal to the mean free path, and this molecule has a tangential velocity. So if you want to calculate what we call the slip velocity, it's the medium value between the tangential velocity of this molecule and this one. It's a statistical approach. And the mean tangential velocity of a molecule at a distance of a mean free path of the wall can be linked, assuming a continuity of the velocity profile, to the tangential velocity of this molecule, like that. And if you enter this equation in this one, you obtain this equation that more or less is this one. We are on a flat wall, so there is only this term, but this term is always present. What we can see quite easily by writing the equation in a dimensionless form is that this velocity slip is totally negligible when the channel is big, but when your channel is very small, this slip can be of high significance and can multiply your flow rate by a factor of 2, by a factor of 10. So this model has been improved by Maxwell, assuming that a real wall is not a specular wall nor a diffuse wall, and that a fraction of the molecule will behave as if the wall was a diffuse wall, and the other fraction as a specular wall. And Maxwell obtained this kind of equation, and first expression of the viscous slip coefficient, which depend on this fraction, which is called the tangential momentum accommodation coefficient. And more generally, this can be generalized in a curve wall. The second term we have seen, or the third we have seen, is the temperature jump. The question is more or less the same. You have hot molecules that can interact with a colder wall, and you can have a short interaction. So if the interaction is very short, the molecule keeps its kinetic energy, so it keeps its temperature. But if the interaction is more long with the wall, it can exchange energy with the wall, and its temperature can decrease. So we can also define a fraction that behaves as if the wall was diffuse, and the other fraction as if the wall was specular. And this coefficient is called the thermal accommodation coefficient, and this can lead to this equation that links the temperature jump to gradient of temperature in this direction. So we have the form that I have given previously. The last term I had spoken about, and I will show you some specific application of this term, is the thermal creep or transpiration term due to a temperature gradient along the wall. If you assume a wall with a temperature gradient. So with a hot region and a cold region, it means that the gas molecules in the channel here are hotter than the cold molecules here. And if you make a momentum balance on a small area of your wall, you consider that some molecules are colliding this wall coming from the hot side and from the cold side. These ones are hotter, so they travel more rapidly, they are a higher momentum, and they will transmit to this small area a higher momentum than the molecules coming from the cold side. As a consequence, at this level, you will transmit, the molecules will transmit to the wall a net momentum from right to left, and by action-reaction principle, it means that the wall will transmit to the gas molecules a net momentum from the cold region to the hot region. So molecules will creep from the cold towards the hot region. And for generating this flow, you do not need any pressure difference. Once again, it's always the case where you are in this configuration, but in a big channel, this effect is totally negligible. In a small channel, it can be very significant and can be used for pumping gas. Okay, so it was a rapid look on the theory, but behind this theory, there is a crucial need of experimental data. Because if we focus on this specific slip flow regime, you have seen that there are these three terms: viscous slip, thermal creep, and temperature jump. And behind the models we can have to describe these effects, there are a priori unknown parameters: viscous slip coefficient, thermal slip coefficient, temperature jump coefficient. And behind them, there are the tangential momentum accommodation coefficient, the thermal accommodation coefficient. So there were, in the last decades, a lot of numerical and theoretical developments on these various models, but there are very few experimental data to validate them. So I will show you more specifically what we can do on velocimetry. I will not have time to speak about temperature. It could be another subject. So what can we do when we want to make velocimetry in a very small device, in a microsystem? A technique which is well known is micro-PIV, micro-particle image velocimetry. It works very well with liquids. You have to seed the liquid with some small particles, and you take two images with two times between the first one and the second one. And typically, you make a segmentation of your image, and each small area like that, you are able to recognize a pattern of particles at time t0, to see by autocorrelation analysis the displacement and also the deformation of this pattern, and deduce for this small region a velocity direction and intensity. It works very well with liquids, but for gases, it would need to have very small particles, typically between 100 and 300 nanometers in diameter, in order to follow the flow of the gas. But these very small particles would be subject to the Brownian motion of the gas molecules, and you are not able to follow a pattern of molecules. So it's not at all efficient with gases, but it is efficient for liquids. For this reason, we try to develop in our group another approach, which is the molecular tagging. Instead of seeding the gas with particles, we seed the gas with gas molecules, and we use molecules that are able to emit some luminescence once they are excited by UV laser light. This is an example. This was made in a liquid because it's also efficient in a liquid. It's the first tag line in a microchannel, and after some time, you can see the luminescence of the molecules, and you can see a profile of displacement of these molecules, and you can deduce a velocity profile. The limitation for gases is that you have much less molecules, and especially if you want to seed, for example, let's say a flow of argon with some tracer molecules, the number of tracer molecules will be very low. And in addition, you have a high molecular diffusion that makes that the initial tag line will diffuse a lot and will be difficult to analyze. So the main constraint to design an experimental setup to make molecular tagging velocimetry will be the spatial resolution, and it is limited by the size of the laser beam. Typically, it's difficult to have a good laser beam smaller than 30 microns in diameter. So if you want to scan a microchannel which is 10 microns in depth with a so larger laser beam, you cannot do anything. So the idea is to increase the size of the channel and to decrease the pressure, to be in the same regime with the same Kilton number, because we have seen that we can, to reach rarefaction regime, either decrease the dimension, either keep larger dimension and decrease the pressure. So it's what we try to do by using what we can call Knudsen analogy. So for that, we decided to work with typical rectangular channel with a depth of 1 millimeter, 1,000 microns, and 5 millimeters in width. The second question is what are the available luminescent tracers? There are not a lot. There are ketones in gas, acetone or diacetyl. The absorption peak of acetone is to 70 nanometers, so it's close to the wavelength of a quadruple ND-YAG laser, so it is interesting. But you can also use a diacetyl, which is less easy to manipulate. So we made our first experiment with acetone, and we tried to excite the molecules with a quadrupled ND-YAG laser. So when you will take a molecule which is at a certain level of energy, when you will receive photon sent by the UV laser, it will be excited, so it will reach a first level. According to the local level, it will relax by vibrational relaxation, and it will come back to the initial energy level, either by realizing a photon very rapidly, it is fluorescence, or by non-radiative de-excitation process, which are not interesting for us. The other possibility is that you pass from the single state to a triplet state by intercrossing system, and once again, from this state, you can come back to the initial state by releasing luminescence. This time it's phosphorescence, or by non-radiative de-excitation. Fluorescence is a very intense phenomenon, so we will have a high intensity, but a very short duration of luminescence, typically a few nanoseconds. And phosphorescence will have a low intensity, but a long duration, and it will be useful to be able to follow the displacement of our molecules. So this is the global scheme of our setup. You have a bubble of gas, which is seeded by acetone, by bubbling in liquid acetone, and then we enter in our channel. We can tag the molecules from this direction and see in the depth of the channel the luminescence of the molecules using a camera with an intensified relay optics, because the signal is very low. It looks like that. If you just tag molecules and take an image, you see that. That is roughly nothing because the signal is very low. If you are able to tag a lot of time and to synchronize the information you receive after some delay, you can obtain this kind of image, which have been done by 25,000 shots. And here you can see a displacement. The flow is going in this direction.
Aquí sí está en mute, lo pone. Hace 10 minutos estaba. El canal está ahí. Ha salido este y digo, bueno, pues toma esto. Y resulta que este tampoco va. He comprado una pila, ya se cambia por si acaso. Podría reinicializarlo, pero ¿cómo vamos a hacer? Lo hemos reiniciado también. Ahora mismo lo acabo de reiniciar. Hemos hecho todo. Hemos reiniciado esto y el equipo de audio. Le he dicho a Dani que tiene que ser. Sí, pues ahora dáselo. Y ahora sí se oye.
Yeah, yes, of course. I didn't discuss about the theoretical points behind this. Of course, we are following our tracer, which is acetone. We have seen experimentally that the profile we obtain when we use molecules with similar mass, argon, that the profile that is provided by acetone, especially in non-rarefied cases where we are very accurate, is exactly what we expect with flow and properties of a mix of argon and acetone. And finally, we are quite surprised to find more or less the same with helium, because there is a high contrast of mass. But of course, the next step is to analyze this interaction between light and heavy gas by, for example, direct simulation Monte Carlo, because with this numerical technique, we are able to put all two gases at the same time and to follow the interaction between both kinds of molecules and to see what is the velocity profile of one gas and the other. Up to now, we did not enter in detail in this question, but it is one of the next one we want to enter. But it seems to work quite well, but for the moment, I agree with you, it's still preliminary.
Okay. So there are no more questions. Let's thank again Stéphane.
Thank you.